Hello everyone, so today I would like to talk about the generation of cave networks in the context of virtual worlds. So caves are particularly interesting because of their wide variety of landforms. They have complex networks with tortuous paths underground, the geometry of the tunnels is hugely varied and detailed, and all of this makes the modeling of cave networks a difficult and interesting task. By the end of this presentation, hopefully you will have an idea on how to generate realistic cave networks with an isotropic shortest path and how to synthesize detailed geometry with implicit surfaces. So let's start by using the correct name for a cave, which is actually a karst. So formally, a karst is a topography formed by the dissolution of soluble rocks, such as limestone. It is characterized by complex underground networks of tunnels and chambers. Karsts are formed by complex physical processes, including percolation and fracturing. They are the result of various geological settings, including the presence of the water table, Inception Horizon, and fracture distributions. As a result, the topology of the network and the shapes of the tunnels are varied, as you can see here. Our goal is to come up with a method for modeling large-scale karstic networks, as well as the detailed geometry of the tunnels. With all that said, our technical contributions can be described as follows. First, a geological framework for synthesizing large karstic networks. Second, an implicit modeling approach for generating the tunnel's geometry. So our pipeline can be described as follows. First, the user provides an initial height field terrain H and specifies the geological parameters, such as the active water table and inception horizons. Then, the user prescribes key points, which can be sinks, springs, or waypoints inside the bedrock. From these inputs, the network generation proceeds in 3 steps. We first generate a 3D geometric graph connecting those key points using an anisotropic shortest path algorithm, taking into account the geological settings. The second step generates the large-scale skeleton of the karstic networks using a 3D gamma skeleton approach. The key point is that our approach is gridless. We adaptively sample space to ensure that our geological features are correctly represented. The network is then amplified with dendritic structures and finally labeled according to its geomorphological properties, leading to an amplified skeleton S tilde. Finally, we synthesize the volumetric model by constructing a signed distance function, representing a signed distance bound to the surface. So before going into the details of our method, please note that the source code for generating the karstic networks is available on GitHub. Now that you have an idea of our pipeline, let's see how we compute a path between 2 points. So we aim at solving a discrete version of the continuous anisotropic shortest path problem. So we need to discretize our domain into a finite set of samples. In fact, sampling is a crucial step for approximating our problem. And uniform grid sampling leads to aliasing issues, and you also have no guarantees that the resulting path will follow the geological features. We propose to solve this issue by performing an adaptive sampling of the bedrock according to its geological characteristics. The construction of the sample set Q is done as follows. We first initialize it with key points provided by the user. We then distribute samples for every important geological features, such as horizon in the figure. And the rest of space is finally filled with a Poisson sphere distribution. The final graph G is constructed as the nearest neighbor graph connecting the samples in Q. Now that we have our graph G, we need to define the cost function for a given point in space and in the given direction. Our cost function is anisotropic and defined as the sum of several terms. The first one takes into account inception horizons. So you can think of an horizon as a very large fracture spanning dozens of kilometers. They are important because karsts tend to develop along those particular Inception horizons. We define the cost as a function of the vertical distance to the nearest horizon. And as you can see, the network on the right developed around the elevation of the horizon, represented in blue. Another important factor for karstic system is the presence of fractures. A fracture is a break of continuity in the bedrock. They can have various orientations, and tunnels tend to follow local fracture orientation. In our system, the user can specify a distribution of preferred tunnels orientations. The cost is then defined using a dot product between the direction at point P and the direction of fracturing. Here, the user specified axis-aligned fractures, which lead to axis-aligned tunnels. The last important geological parameter is permeability. So permeability expresses the capacity of a rock to let the fluids circulate through its pores. We do not model the physical permeability. Instead, we use a qualitative parameter expressing the relative resistance to water. This is the function pi. For more details about how this function is defined, I refer you to the paper. On the right, the user placed two permeability spheres, which leads to tunnels passing through this highly permeable volume, as the cost is the lowest here. The next step of our pipeline is the computation of a geometric graph, the actual skeleton of the karstic network. Put simply, our goal is to compute the karstic skeleton S from the set of key points P using a non-Euclidean metric. To do that, we proceed in two steps. We first compute the complete graph between all key points in P. Then, we perform pruning using an empty region criteria based on a 3D gamma formalism. The pruning works by defining a parameterized neighborhood around the path from a point A to point B. So the neighborhood is defined as all the points P where the distance from A to P plus the distance from P to B is inferior to the distance from A to B. So the criteria for keeping the path AB is that no other key points should be inside the neighborhood. The gamma parameter currently circled on the slides is provided by the user, and it influences the size of the neighborhood. When gamma is small, the neighborhood shrinks and more paths are kept by the algorithm. So we generated a large-scale skeleton S, which is rather coarse, and we amplify it by distributing new points stochastically in the domain. These points are then linked to the existing network by performing multiple anisotropic shortest paths. Finally, we perform midpoint subdivision algorithm parameterized by a tortuosity factor. Each tunnel section in the mesoscale skeleton S tilde is then classified according to its geomorphological properties. The last part of our pipeline consists in synthesizing the detailed geometry of the tunnels from the labeled karstic skeleton. More precisely, we want to generate an analytic implicit surfaces defined as a continuous one Lipschitz sign distance function that defines an upper distance bound to the surface. This property is crucial when rendering an implicit surface, for instance with sphere tracing or mesh extraction. Our implicit surface is defined as a hierarchical construction tree, combining operators as internal nodes and primitives as leaves of the tree. Therefore, we generate an implicit primitive for the tunnels and combine them with the base terrain using a difference operator that will carve everything. So I will not go into the details of the terrain function, but please note that there is some work to be done to ensure a one Lipschitz sign distance function for a height field. Instead, let's focus on the tunnels function. Our goal is to generate an implicit primitive for a 3D curve. We must be able to deal with asymmetric cross-sections as identified in geomorphology. However, defining such a primitive for a sweep object with cross-sections along a curve is not possible in the general case. And this is particularly true when the curve has a high curvature because of discontinuities in the distance function. Therefore, we use a more general approach. For straight or almost straight tunnel sections, we use a sweep primitive. And for more tortuous paths, where curvature is high, we use unions of spheres. This scheme guarantees that we keep a continuous one Lipschitz function at the cost of additional memory because of the need for instantiating a large amount of spheres. I will not go through all the details here and invite you to read the paper for more information. Instead, let's go on to the results. Our sweep primitive is versatile and can reproduce a wide variety of tunnel shapes as identified in geomorphology. Here is an example of a canyon tunnel which appear in the Vadose part of the cave above the active water table. This bed tunnel is partially filled with water inside the phreatic part of the karsts. On the validation side, we compare the output of our method with real karstic networks. We show that our networks are consistent with real ones regarding several characteristics on the graph of the network. Furthermore, we validated our results with an expert in geomorphology who is one of the authors of the paper. To conclude, we presented a geological graph-based method for synthesizing realistic karstic networks. We showed how to generate the detailed geometry of the tunnels with an implicit modeling approach, introducing new primitives and operators. As future work, some part of our pipeline could be replaced with better heuristics as knowledge in geomorphology evolves. Some work can also be done on the optimization of implicit primitives and operators to improve field function evaluation time. And finally, the most promising thing to me is about cross-domain work. So this paper is a result of a collaboration between computer scientists and geomorphologists, and it has been super interesting to share knowledge and collaborate, and we are still working with them on new, promising topics for the future. To conclude, please note that the source code for the generation of karstic networks is available on GitHub. Thank you for your attention.